Next speaker is here, Professor Tim Baldwin. So we'll keep the bio short, but there is a lot of things to say about Professor Tim. And so Tim Baldwin is a Melbourne laureate professor in the School of Computing and Information Systems, the University of Melbourne, and the director of ARC Center for Cognitive Computing in Medical Technologies and vice president of Association of Computational Linguistics, ACL. His primary research focus is on NLP, including social media analytics, deep learning, and computational social science. So Tim completed his BSc and BA at the University of Melbourne in 1995 and M Engineering and PhD at the Tokyo Institute of Technology in 1998 and 2001. Prior to joining the University of Melbourne, he was a senior research engineer at the Center for the Study of Language and Information, Stanford University. His research has been funded by organizations including Australia Research Council, Google, Microsoft, Xerox, ByteDance, Seek, NTT, Fujitsu, and has been featured in MIT Tech Review, IEEE Spectrum, The Times, ABC News, The Age, Sydney Morning Herald, Australian Financial Review, and The Australian. So he is the author of well over more than 400 peer-reviewed publications across diverse topics in NLP, AI, with over 17,000 citations and an H-index of 61. So in addition to being an ARC fellow and the recipient of a number of best paper awards at top conferences. So it's again a pleasure to invite Professor Tim and to speak in front of all of us. Thank you. Yeah, over to you, Tim. Thanks.
Great. Thank you for the kind introduction. Let me share my slides. If you can just confirm slides are visible and we're actually,
yeah,
so that should show the second slide now. We were having issues yesterday.
Yeah, all okay.
All okay. Excellent. Thank you. So it's a great pleasure to be able to join you in this fantastic event, IndoML.
It's not full screen.
It's not full screen. Okay, hang on. Try again. That should now be full screen.
No.
So what are you seeing?
No, we are seeing on the left side introduction, baselines, etc. also. And on the right side, we are seeing create PDF.
Oh, how odd. Not sure why. Let me perhaps remove that. Odd that I can see it in full screen, but none of you can. Oh.
I think you have to put it into full screen mode.
Should have been doing that before. Is it workable as is, or?
Yeah, it's workable, but the right side is still seen. The left side has gone.
I'm not sure how to. I see. I can just drag this over. So yeah. I tend not to use this iMac for anything other than giving presentations. So I'm not sure how to remove the right-hand bar.
So are you sharing the screen or you're sharing the application?
I thought I was sharing the screen, but let me try again. Oops. Okay, let's try this then to see if this is any better.
Yeah, this is perfect.
Okay, I don't quite understand why they didn't work, but excellent. We got it to work. Let me start again. So Tim Baldwin from the University of Melbourne, delight to be here. Cruelly scheduled alongside the first innings of the second Ashes test, I might note, but that's all right. As long as there aren't any comments in Q&A relating to wickets, we're good. Okay, so this talks all about fairness in NLP. Obviously, this is a very big topic nowadays, and I won't be able to do it true justice. This is very much centered on a series of papers that we've developed over the last 3 years or so. There are lots of references, if you go to those papers, to the broader literature. So forgive me for being slightly egocentric in how I'm presenting some of the work today. So when we talk about fairness, what sorts of things do we mean? Just to give us a taste of the topic for those who are unfamiliar. So in a broader AI context beyond NLP, real-world examples, very recent real-world examples would be starting out with Twitter's auto-cropping algorithm. There'd been a lot of banter about whether it was biased or not. To Twitter's credit, they actually had a prize, a bounty for people who could expose biases in their auto-cropping algorithm. They ran themselves back in August of this year. And the winner of that showed that indeed the auto-cropping algorithm tended to select faces in images that were slimmer, younger, lighter colored skin with warmer tones. So obviously we've got an issue here in that it's going to select people of particular types and particular backgrounds and particular racial heritage, say, over others. So hence unfair in the sense that for no fault or no sensible reason other than the bias in the model, the auto-cropping algorithm is going to select particular individuals. So that would be in a vision context. In a sort of more general machine learning context, also earlier this year, back in August, there was an expose of automatic mortgage approval algorithms in the US. Basically doing a manual version of counterfactuals, showing that if you provided the algorithms with basically all of the same features in terms of the person who was applying for a loan, with the exception of one critical feature, something like gender or their racial profile. So we've got the example here of white versus Latino, given this is the US context. You would have a flip in the label. So if the applicant were white, they got the mortgage approved. If they were Latino, they did not, despite the fact that all the rest of the details of the mortgage approval were identical. So obviously significantly biased in terms of race and to a lesser extent other attributes. And again, inalienable properties of the individual, something that would legally be considered racial discrimination. One that's very close to home to me and was possibly the road to Damascus moment personally in terms of my own research was in the context of language identification, a topic that I've worked on and off over the years, where this is at Stanford, David Jurgens and colleagues at the time took a number of different language identification libraries, ours being langid.py in the blue there, and tested their recall. So basically sort of said, look, if we were using language identification libraries for health monitoring purposes, the way over Twitter, the way we would be doing it is by pulling out all of the English, in this particular case, tweets for different countries and running them through some system. So let's look at the recall of these different methods for English tweets across different countries and break down the results based on the Human Development Index of those different countries. And what you observe is this very confronting drop-off in recall based on the Human Development Index. So, a English variety like Nigerian English is going to be all the way over on the left here, whereas something like Australian English is going to be all the way on the right, which is a dreadful thing to think that a system that you have developed has as a bias. langid.py was developed well before people started systematically looking at fairness, but even so, it's going to perform a lot better for a certain category of population than for a different population. So to step back a bit, what is fairness in the context of NLP? So we tend to distinguish between source and target bias. So it's NLP, obviously, it all relates to text. And fairness tends to be in terms of, is it about the person who's written the text, so the source, or is it about the target, the person or the group about whom it is written? So if in this particular example, an excerpt from a movie review, if we read it, it's an adventure which reaches back to Golden Age Hollywood and the devil may care world of Douglas Fairbanks and Tyrone Power playing Zorro, or Errol Flynn playing Robin Hood. If I were to present you with that and ask you to predict what is the binary gender of the author, what is the country they are based in, what is the relative age of that person, you would probably predict that it's a male, more likely British than American, and probably an older male. And it's all sorts of subtle things. The devil may care, a very particular expression which would tend to be used by an older person. Or I'm talking about Golden Age Hollywood, obviously someone who romances about a particular era of Hollywood, for example. And you'd be right. So this is written by someone called Peter Bradshaw, a Guardian movie reviewer who's about 59 at the moment and grew up in England. So there are lots of subtle signals in the text on the basis of the background of the author across all sorts of dimensions, which our models pick up on, and that leads to issues with fairness. I'm primarily going to be talking about source fairness, but just by way of mention, target fairness is something like, and this is taken from the GAP data set from Google. So we've got, it's a slightly confronting example. Eliza Bryant was born in North Carolina to Polly Simmons, a slave, and her master. So the task here is to disambiguate or do the anaphora resolution over her, the pronoun her, as in, is it Polly Simmons we're talking about, or is it Eliza Bryant? The answer is Polly Simmons, and the point of the GAP data set is to expose the fact that co-reference resolvers and pronoun resolution systems tend to perform much better over male English pronouns than female English pronouns. But the point here is it's not about who wrote it, it's about the reference, the particular individuals who are mentioned in the text. Okay, so the sorts of predicted attributes, as we will call them, of interest, so inalienable properties of the speaker, which are getting picked up on by our models and leading to these disparities in performance. It can be all sorts of things. So it could be something like gender. We'll tend to look at it as binary gender, more for machine learning convenience and availability of data rather than anything else. Race, which you tend to sort of get into very messy territory in terms of some of the nomenclature here, as in what is race? Is it more of a cultural thing than a genetic thing? And yes, there's all sorts of discussion to be had here. So we tend to follow whatever are national norms and acceptable labels in different contexts in terms of what does race actually mean. Age, in terms of ageism, although it tends to be reverse ageism, as we'll see, sexuality, all sorts of things. So it could be something like the interaction between hate speech and race, either source or target. It could be the interaction between the properties of the author, so age, gender, country, as we talked about with our movie review example, and ratings, say, and the ability of our models to predict the ratings for a product review or a movie review or whatever it's doing, or morphosyntactic analysis, or there are various contexts that people have looked at this in, either in terms of source or target fairness. Okay, so our primary focus today is going to be on algorithmic approaches. How do we mitigate bias? How do we train our models to be fairer? We're never going to make them perfectly fair, but we can at least hopefully do a better job through explicit training of different types. So, for those who are perhaps unfamiliar with the topic, a natural thing to ask in the first instance would be, well, surely if we don't expose any of the protected attributes to our models at training time, they're going to be fair, right? So, this idea of fairness is blindness. What could possibly go wrong? And the answer is, well, for all sorts of reasons. In NLP, it could be because of the pre-training of our models and sort of baked in linguistic biases or sampling biases in terms of the data that our models have been pre-trained over. But it can be all sorts of things as well. What tends to happen is that our models would tend to pick up on these subtle biases and actually amplify them. So make them worse than they are in terms of label imbalances or imbalances in the distribution of protected attributes in the source data. So it tends not to work. It's a bad idea, or just sort of blindfolding yourself to the problem doesn't make it go away. Sort of a slightly more motivated approach might be to say, well, if it's a simple question of imbalance in the data set, there tends to be a little bit of a mentality perhaps of, well, the issue is with the data, it's not with my model. So if I can fix the data, the problem is solved, which is very often not the case. The problem is much more complex than that. But if we take that line, then if we balance our training data with respect to our protected attributes, surely that will lead to fairer models. So we're going to use this kind of cartoonish rendering of the setup of models with the box at the bottom representing our training data, where our predicted attributes here are going to be color to sort of try to pick a neutral context to talk about predicted attributes in. So if we have an overrepresentation of blue objects and underrepresentation of purple, we'll simply downsample the blue training instances so that we have balance between our purple and blue, and surely this is going to solve our problem. And the answer is no, for lots of reasons. So it tends to drive down overall performance, particularly when we have severe imbalance and underrepresentation of particular predicted attributes, because we're going to hobble our models in terms of the amount of training data they have. So it's not just that you get low accuracy but fair models, the fairness still you tend not to achieve. So it's slightly better than perhaps fairness as blindness, a blindfolded first take, but not much better. Okay, so how can we do better than that? So I'm going to focus primarily for the purpose of this talk on adversarial methods, and I'll come back at the end to talk about a much broader range of methods that you could use. What we want to achieve is models which are as good as possible at capturing whatever the concept that is associated with our target variable is, and as bad as possible at recovering whatever our protected attribute or attributes, there can be more than one, are from whatever representations we're generating with our models. And the way that we're going to achieve that is through adversarial learning. Okay, so coming back to our cartoon representation, what we want to have is models which are good at predicting what are elephants and what are rhinos, but which are just hopeless at predicting the color. And we're going to explicitly use the protected attributes in our training data to train our models to try to achieve this. And ideally in such a way that we don't drive down the performance with respect to our target variable. Okay, so what does this look like? So that the sort of simplest version of this is we have whatever base model, a transformer, a CNN, whatever we choose it to be, or a simple logistic regression model. It can be anything at all. And we then have, we're predicting our target variable on the basis of whatever representations we're generating through our base model. And then we have one or more, depending on how many protected attributes we have, so one each, adversarial discriminators, which have the job of predicting relative to the hidden representation, the particular value for each of these protected attributes. So in our rhino and elephant example from before, we would have one of these predicting the color. Is it blue or is it purple? And the way that we train our model is via this minimax formulation. So we're trying to minimize our cross entropy as per usual. But at the same time, we're trying to maximize the cross entropy over our target variable, but maximize the cross entropy over our protected attributes. Okay, and we're going to have separate models for each of these two, but which are connected via the hidden representation. So both our base model and our adversarial discriminators are going to be back propagating, in the case of deep learning models, through the same hidden representation to achieve this. And in terms of training the models, it's not going to be differentiable as a minimax problem. So we're going to have an iterative approach where we fix our discriminators and minimize our cross entropy for the target variable, fix the parameters for the model there, then train our adversarial discriminators in terms of the maximization, and repeat over some number of iterations until we get convergence in terms of our overall loss. Okay, so let's start out with that basic version of adversarial discrimination and test it out over a couple of different contexts, and we'll build on it variously as we pick up on some shortfalls in the basic formulation. So this is work from a couple of years ago now, 2018. So using this, and it's sort of showing its age a little bit because we're still playing around with ByteDance, but in the first instance, we played around with the part-of-speech tagging task, where simple Google University part-of-speech tag set, so a relatively small number of tags. And our interest is, do we observe discrepancies in the accuracy of our model across particular protected attributes? Okay, so we're going to, in the first instance, train our model on sort of general domain text from the English Web Tree Bank. We're then going to further train it on a small amount of Trustpilot data, because we have annotated data for protected attributes in terms of the author attributes for Trustpilot, which we don't for the English Web Tree Bank, hence the two-step training. And then evaluate on Trustpilot in the first instance in domain. So Trustpilot is reviews of sites or brands, but also an out-of-domain or out-of-register, perhaps more appropriately, data set of African-American vernacular English. So from African-American populations in the US, completely different to our Trustpilot data. So partly to see, can we train fairer models in domain, but partly to see in training them to be fairer in domain, do we get crossover effects in quite different registers of the language? Okay, so for Trustpilot, we have age, as in user contributed age. People volunteer their age as part of writing a review on Trustpilot, or a subset of them will at least. So we binarize that, consistent with the earlier work of Dirk Hovey and Anders Søgaard, and binary gender, male versus female. And we're going to look at accuracy in domain. So what we observe is, so the baseline without adversarial discrimination, just the pure ByteDance tagger, we observe the sort of characteristic discrepancy. So we get a fairly small delta in terms of binary gender and a larger delta in terms of age. So harking back to what I was saying before, we get this reverse ageism. Our models tend to do better on the text of older authors because that's what is overrepresented in the training data. Even for sites like Trustpilot. So this delta we want to bring down to as close to zero as possible for it to be a fair model. And indeed, when we do our adversarial discrimination, two things happen. So both the deltas come down, fairly close to zero, which is encouraging, but perhaps more encouragingly, the overall results go up. So we have both a fairer model and a more accurate model. And what we find when we actually do analysis of the output of the model is the patterns in terms of the mistakes our models are making are much more subtle. The models are made to work a lot harder. They can't sort of fall back on sort of cheap heuristics in terms of, if it's a over 45 male who's using this particular term, then it's going to be a noun or a verb. It has to generalize, and in doing so, the errors are sort of much more all over the place, and there are fewer of them. Perhaps even more impressively, what happens when we apply the baseline versus the adversarially trained models, and bear in mind they have no exposure at all to AAV data. So this is a completely held out register of data. So this is a little bit like the Lang ID case that we were talking about before, with different varieties of English from different countries. Say, where we're observing that our results are nowhere near what we get in the IndoML case, but over the different subgenres in this particular data set, our results have been lifted substantially, as I say, without any domain adaptation or doing anything specific for AAV data, simply through this adversarial discrimination, making our models fairer. So, very encouraging result to start out with. And over the task of sentiment analysis, so this is doing the Trustpilot 5-way, how many stars has the author assigned to this particular review based on the text. So again, showing its age slightly, a CNN now with an adversarial discriminator. No great surprises there. The extra predicted attribute of location, in addition to the two that we had before. And so it's balanced across the 5 countries. It's all English text, but from the US, UK, Germany, Denmark, and France. And what we observe is, once again, in terms of our F-score, bearing in mind this is a 5-way task, so that the numbers are quite a bit lower than what we had for the part of speech tagging, is our F-score for the baseline, as in without any adversarial discrimination, versus with adversarial discriminators trained on either individual predicted attributes, so just age or just binary gender or just location, or all 3, so with 3 separate adversarial discriminators, our F-score either goes down a tiny bit or goes up a tiny bit. I wouldn't read too much into that. Here we're measuring leakage. So we had separate results for the delta, similar to what we were doing before, but we're also looking at this question of leakage in terms of, if I separate to my adversarial discriminators, train a discriminator on the basis of the hidden representation to predict the age or the gender or the location, say, how well would my model do relative to majority class? So, majority class performance, or the closer I get to that, the less information, the less demographic information I'm carrying across, meaning my adversarial discriminators are doing their job. So, we want these numbers to be as close as possible to the majority class numbers, if we're truly bleaching out that information, which is largely what we see across the diagonal, age versus age, sex versus sex, location versus location. And with all 3, to some degree, we sort of do not quite optimally perhaps for the individual ones, but certainly across the board. We've removed a lot of the demographic information in doing this, and we've got similar sorts of results for the deltas. So, encouraging at this point, fairly simple architecture, but it seems to be very effective. So, kind of all rosy at this point. And there's a but. So when it works, it can work very well, but there are some caveats. And the major caveats with adversarial learning are instability, and related to that, the difficulty in getting the model to train sometimes, or its failure to converge. So what you tend to have is highly non-convex decision surfaces, and the model is getting stuck in all sorts of strange sinks at times, particularly for more complex models and more complex tasks, meaning it can be a little bit unpredictable whether when it works and it converges, it will tend to work well, but sometimes it just won't converge. So what do we do? So work from Yoav Goldberg and one of his students at the time, as a follow-up to our work, came up with a couple of sort of engineering solutions. So one obvious thing would be to add extra capacity to the adversarial discriminator so that it can do a better job, or upweight. If you were paying careful attention before, there was a weighting term, a lambda. In fact, there's one lambda for each of our adversarial discriminators for each of our protected attributes. So if you upweight those, then they're going to have more impact and it will tend to converge better and perform better. Or you can ensemble them. And what they found in sort of doing a systematic analysis of this across different tasks was, these all sort of work to some degree sometimes, but there was sort of no one killer approach which sort of worked across the board. So there was, things were better, applying some of these engineering tricks, but still, this inconsistency remained. So this then leads into more recent work of ours from EACL at the start of this year, in terms of saying that, well, when we're ensembling our discriminators, so basically what we're doing is we have k discriminators instead of one discriminator per protected attribute. And of course, you could have different numbers of discriminators for different protected attributes if you wanted to. There's nothing to insist that you have exactly the same number, but just to keep things simple. And we're going to, rather than just naively having an ensemble and kind of leaving it up to chance that our individual discriminators are going to capture different things and complement one another, we're going to add a constraint, in particular an orthogonality constraint on the parameters of the adversaries within a given ensemble. Okay, so for each of our protected attributes, we're going to have this orthogonality constraint where we calculate the dot product between the respective hidden representations across the different adversaries, and calculate the squared Frobenius norm on the basis of that. Sorry, not the dot product, the inner product. One advantage that has been pointed out for this style of approach is it tends to both encourage the hidden representations to shrink to zero, but also discourage the model from just learning sort of rotated orthogonal representations from one another, which are sort of functionally equivalent to each other. Okay, so let's apply this and see if it helps in terms of both the performance, the relative fairness, as well as the consistency of our approach. So there are a couple of different experiments, but I'm going to focus here on sentiment analysis. It's a simple two-way sentiment analysis now on the basis of the Moji data set. Our predicted attribute here is going to be kind of race in very heavy scare quotes in terms of African-American English versus Standard American English in the writing style. And we're going to look at, once again, this trade-off between the accuracy of the model and the gap in terms of the true positive rate and the true negative rate gap between the different values that we have for our protected attributes. And here we're back to just one protected attribute. The number will go up and down a little bit, as well as leakage similar to what we did before. Okay, so jumping to the results, what we have here is the simple standard model based on the deep Moji pre-trained model in the blue versus a simple ensemble without any constraints in terms of the component models within the ensemble versus the differentiated ensemble with this orthogonality constraint. So what we observe is, in terms of raw accuracy, we're actually getting slightly higher performance, but importantly, lower standard deviation. So sort of more consistency in our models, which is good. Our gap is coming down substantially relative to the base model, and also much better, and again, much more consistent than the naive ensemble. And same number of parameters, same number of discriminators that we have in each case. So the numbers are directly comparable. The only thing we have is this orthogonality constraint. And leakage, much for much, it's come down ever so slightly. There's so much bias in the deep moji pre-trained model that it's very hard to bleach much out of this particular model in terms of leakage. But in terms of gap between AAE and SAE, in terms of true positive rate and true negative rate, we're seeing substantial improvements. So that's good. So ensembling works, and ensemble, and we also had results for a single discriminator, which was worse again. Orthogonality definitely helps out. So again, all good, sort of sounds encouraging. The next thing we're going to think about is, okay, this is all sort of well and good if you have protected attributes for all of your training instances at training time. We don't need anything at test time in terms of inference, but at training time, we're, in our experiments up until now, we've been relying on having fully annotated data. What happens though in the sort of more real world setting where for some instances we have access to protected attributes and for others we don't, because of whether it's confidentiality issues or user disclosure. Some users have chosen to disclose protected attributes, others haven't. So we've got partially labeled data in terms of our predicted attributes. Can we still train these models? And the answer is, well, if you think about it, because we've decoupled the training of our adversarial discriminators and the base model, we can. We can trivially just train the discriminators on the subset of instances where you have protected attribute labels. Easy. And if we think about it a little bit more, we can also pick up on the fact that we could transfer protected attributes from a completely independent data set if we so wanted. So we don't have to have any labels at all in terms of our predicted attributes. We only really rely on labels in terms of our target variable. But if we know there are particular predicted attributes with their potential sensitivities, we can potentially use data from an external domain for the training there. So let's start out with the case of the partial labeling in domain. So again, sentiment analysis. So what we have here in terms of plots is we're playing around with our lambda hyperparameter. We're comparing our accuracy versus our gap. So lower is better for gap, higher is better for accuracy, of course. And what we have with the different lines is we've either got 100% or 50% or 10% or 1% of the data, which is labeled with our predicted attribute. And what we see is, we get this intriguing result that the particular lambda based on the relative amount of labeling varies, we don't get much of a difference in terms of accuracy as we would expect, because the target labels are the same. It's only the protected attributes that have changed. But we can get very similar values in terms of our gap with a lot less data. And we can also look at this in an out-of-domain setting where we've got, instead of elephants and rhinos, so we know nothing about colors for our elephants and rhinos, we know about colors of whatever other random objects. And that's what we're going to train our adversarial discriminators over. When we do that using sentiment analysis task, but predicted attributes from a H-speech data set, we get the results that we see here, where the circles are in domain based on 1% of the data being labeled with predicted attributes. The crosses are out of domain, so we certainly get a reduction and a higher gap for the same accuracy, but relative to the blue line here is the baseline of, if I have just a uniform Bernoulli random variable, and I basically just randomly label my training instance with protected attributes. How well do I do? I certainly do much better than that, and get what aren't completely useless results. So it works to some degree. Whether this is good enough for a particular application, of course, will depend on the specifics. So very small amounts of in-domain data go a long way. And fully decoupled training is certainly something you can do. You're going to take some sacrifice in terms of your target label accuracy just because of domain differences, but it can work, and we've got extra results in terms of trying to do sampling of the particular instances we use. I refer you to the paper for that. That was an ACL findings paper. So the last thing that I want to talk about, and we started a little bit late, so I assume it's okay to keep on going, but let me know if not, is intersectional bias. So what I mean by this is the way that we've trained our models to date is to say, okay, for a given group, so binary gender, for example, we have a single adversarial discriminator, which is doing, in all of our examples to date, binary, it could be multi-class labeling of that particular attribute. So if we had two protected attributes, binary gender versus race, say, or color, we would have two separate adversarial discriminators, which are completely independent of one another, except the fact that they're both backpropping through the same hidden representation. But there's no sort of explicit structure that we're applying to those two. Where if we think about it, so that, that's the version of looking at our data in terms of the independent groups, looking at the individual rows and columns, or it can be a tensor, I guess, if we've got more than two protected attributes, but not at the interactions between them. Where we can, of course, look at the intersectional groups, where we look at white males versus white females versus male people of color, etc. Where we're going to get, in the binary case at least, a lot more combinations as we add more and more protected attributes. So this is going to be the equivalent of sort of summing up the cardinality of each of our protected attributes. This is going to be the product of the cardinality of all of them. Or we can also go to what's called gerrymandering intersectional groups, where we look at the overlapping subsets defined by the intersections of all of our private attributes. So we have each of our rows and columns, but we also have each of our intersectional groups. So we end up with a slightly higher number again of combinations, because we sort of have the wildcard version that we throw into the mix. And we can use this insight either to simply represent our data. So we form groups over our data, and we can train our adversarial discriminators on the basis of these different groups. So gerrymandering groups versus intersectional groups versus independent groups, say. Or we could use it for evaluation. So we can look at gap with respect to these different groups. So up until now, we've only looked at gap with respect to independent groups. We can also look at gap with respect to our other groups here. The question here is, so when we evaluate, not just based on independent groups as we have up until now, but also intersectional and gerrymandering groups, how well do they perform? And if we do direct optimization in terms of intersectional and gerrymandering fairness, basically through this data partitioning trick by constructing these overlapping groups, how much of a gain do we get? And in the adversarial case, it's a simple extension. We just have more adversaries because we have more groups. I'm going to have to skip over the details. So there's a bias constrained model that we could think about here, where we have explicit constraints in terms of, based on whatever fairness criteria across each of our groups, we want the absolute difference between the performance for a particular group and the aggregate performance to be as small as possible, as in bounded by a slack variable, and use constraint optimization to train a model, but I'll have to skip over the details there. Just jumping to the results that we have here, what we observe, so this is now in the context of a biography data set, we're predicting the occupation, nurse versus surgeon in this particular case, with protected attributes of binary gender and economic status, we actually find, and there are details in terms of model selection that I would have to refer you to the paper for, but the red bars here are the bias model, as in simple, no fairness training at all. So our maximum gap in the worst case for a particular gerrymandered group is very bad. Whereas in our adversarial models, when we train them either based on the intersectional or the independent, or the intersectional or the gerrymandered, so these three different versions of the groups, we actually don't get much of a difference. We get very small improvements in terms of average gap. Partly because of the trade-off between the complexity of the model. We have more and more adversarial discriminators against the expressiveness in terms of the different groups. And the constraint-based model tends to do ever so slightly better, but it's a much more complex model and less versatile, shall we say. So again, our adversarial methods have worked remarkably well, even without explicit training in terms of intersectional gerrymandering groups. They lead to improvements in terms of fairness with respect to gerrymandering groups, which is impressive. And there are extra results for other methods in the paper once again. Should I be finishing up at this point, or?
I guess yes.
Yes, that's fine. So let me just mention, and I'll share the slides, and you can look at the slides separately. So sort of big outstanding issues are model selection. It's hard, it's unsolved, it leads to all sorts of issues in terms of comparability of results, as well as controlled experimental setups to be able to do careful analysis of under what data conditions do different models perform better or worse. A lot of people use different data sets and, hey presto, my model performs better, where perhaps, under different data conditions, it wouldn't have performed anywhere near as well. And as I mentioned at the start, there are lots of other methods that we've been playing around with and others have played around with, but I will leave you to read about those in the slides. So just to summarize, we've talked about adversarial learning variously, starting out talking about how to achieve better stability through orthogonality constraints, then talking about the versatility in terms of partial labeling or complete lack of labeling of predicted attributes, and then talking about sort of gerrymandering and intersectional bias, and finding that, again, the adversarial technique is actually remarkably robust, even under that more expressive evaluation. And lots more to be done. And I just wanted to have a shout out to my wonderful co-authors, Trevor Cohen, Leah Froman, Shudong Hung, Yitong Li, and Shiva Subramanian, whose work has been presented here. And lots of references that I will leave you to read about in the slides. Done.
Yeah, thanks, Professor Tim. So we have one question from the attendees, and the question is the following: does the adversarial discrimination loss encourages high entropy over the protected classes, or it encourages the model to make a wrong prediction for the protected class?
It encourages them. It encourages high entropy. So it doesn't just sort of flip the labels. It encourages high uncertainty. So sorry, just going back. So we're trying to maximize our well, yeah. I mean, I guess strictly speaking, it's a bit of both. But we because we're maximizing cross entropy, we want it to be as bad as possible. So yes, I guess it is more the latter, making the wrong predictions.
Okay.
Could we model as a multitask learning problem? Yes, we could. It doesn't perform as well in our experiments. Okay.
Okay. So there is just one more from the same attendee. Could we model this as a multitask learning problem instead of an adversarial learning?
So as I say, we could, and we've got various experiments looking at that, but it tends not to perform as well as what we have here. And if you do it simplistically as a multitask learning problem, it tends to make models less fair. You have to have the gradient reversal trick that we're using here is a critical component of it. If it's just multitask learning, you're sensitizing the model even more to some of these differences. So you tend to get a rich gets richer effect.
Yeah. Okay, Professor Tim. So it was pleasure to hear you here, and we are very thankful for you to accept our invitation. Thank you very much.
Thank you very much, and all the best to everyone.
Yeah, thank you. Thank you very much. Yeah.